Hello friends, welcome to Machine Tool Design. Let us continue. So the advantages of power screw or the salient features of the power screw are as follows. They have large reduction which makes them possible to obtain slow travel of the operative element. So therefore the motor can run at high speeds, however the power screws run at slow speeds, so this helps in torque multiplication, also helps in accuracy. Okay. Also they have simple design and compactness, so that is something which is very important, and also they have a very high load carrying capacity. Now this basically comes from the worm and the worm wheel reduction, and also innately the screw jack or the nut and the screw arrangement has a very high load carrying capacity. Also you've got uniform and accurate movement of the operative member. So these are some advantages of power screws, and the power screws may be classified into two types. One is sliding friction, another is rolling friction power screw. In a sliding friction power screw, there is a proper sliding motion between the screw and the nut, and in the rolling friction power screw there will be rolling elements between the screw and the nut, and therefore the design is slightly different, but mainly the design principles are very similar. um, Going ahead, let us try to see and look into what types of materials are used for sliding friction power screw. So here we understand that in order to minimize wear, one principle is very important, is that there must be a combination of hard and soft materials, and that is very good with friction and wear. Okay, so therefore the material of the power screw must have a high surface hardness as given here, and this is very important. If this high surface hardness is not there, lot of wearing can happen on the power screw, and therefore high hardness is there, and this is done by heat treatment and other methods. Okay, at the same time the nut should have a softer surface, so therefore a combination of hard surface and the soft surface would help. So here you see the combination is given here. The nut of the power screws are made of softer materials, and they are mostly being made of generally bronze. Okay, so therefore you will see this type of combination is there. Now in screws also there are different types of materials used. Normal accuracy, you can use something like C45 and C50. Precision power screws are generally made from higher carbon steels, and precision power screws that are heat treated are made from alloyed steels. Okay, so based on our precision and accuracy, the material cost also tends to increase. Okay, so that is something which is very important. Now going ahead, there are different types of profiles of the screws also. So here you can see what are the different types, and the most accurate and the most efficient one is the square thread profile. Okay, so in the square thread you get maximum sorry, you get the maximum area of engagement, and also there are no angles, so generally you get a lot of accuracy here. However, the manufacture of square threads is kind of tough. It's not very easy. It's very difficult to maintain that perfect square profile. So most of the times different types of threads are used. Acme threads with 29 degrees included angle, something like this, they are used, or even a slightly lesser angle of 10 degrees. Okay, so that is also used. So that is easier to manufacture, but accuracy wise they are not as good as the square profile, but however they do get the job done pretty well. Okay, now let us go ahead and look into the design process. Okay, so the design process is something which is very important here. The sliding friction power screws are generally designed for these following things. The first one is wear resistance, second one is strength, third is stiffness, and fourth is buckling stability. Now when an engineer basically thinks of any system, he has to see how the system will function under different types of constraints. and also what type of the what part of the assembly requires what type of design requirements. So the first one is wear resistance. So as you may have guessed it, wear resistance happens between, the wear basically happens between the screw and the nut, and if that area, which is very sensitive, if that is not properly designed, one can get exceeding amounts of wear, galling can happen, and a lot of surface damage can happen, and then the power screw will be rendered useless. So therefore wear resistance should be there, and the proper design must be done for that. Similarly, the strength, that is also very important. The power screw has to carry lot of loads, and therefore it must be designed properly for strength. Also for stiffness, if the strength is good but if the stiffness of the entire assembly is not very high, the object won't fail. However, it will give you unwanted deflections, which are certainly not required. And the last one is buckling stability, because sometimes power screws may have pretty large lengths, and in such cases buckling is a very big problem. As the length increases, the tendency to buckle increases. Please understand, the analysis of power screw is mostly like that of a column, because the forces are acting along the axis of the screw. So all of these four are very important. Okay, so now we will first look at the wear resistance phenomenon. And in wear resistance, the most important thing that is seen here is the pressure. Okay, generally the speeds in the power screw are not very high, so here again we look at just the maximum pressure. If the maximum pressure inside the power screw, especially on the surfaces where the nut and the screw engage, okay, so if that pressure becomes greater than a certain pressure, then failure generally happens, and that is generally based on the type of material pair that is used. Okay, so that is something there. So that is how you will determine this P average. Okay, this one right here, the permissible average pressure on the thread surface. So that is based on the material pair that is used. We will see now, and that is pretty much standardized in different design books. And now we will see how to calculate the pressure that is coming on the thread. Okay, so in order to understand that, just let us try to have some type of visualization, and let us look into this particular diagram. Okay, so it's going to load in just a second. Okay, so right here, now there are various things to understand. Here is your power screw. Okay, and this is the nut, and it has got a certain length of the nut. Okay, the nut is not visible. Basically it is the inside diameter of this is the nut, and the power screw has threads on there. Okay, as you can see here, and then obviously there is the pitch of the thread. Okay, so that is something which is very important. So all of these concepts have to be understood very well. Okay, so what is the pitch of the power screw? Suppose you may have a square profile or an Acme profile, but pitch is very simple. It is the distance between two crests or two troughs. Okay, so that is the distance, that is the basically pitch. And this pitch is very important, because the denser the pitch, that means the narrower the pitch, the more number of threads will be there per unit length of the nut. Okay, so that is something which is very important. Okay, now another thing that has to be understood is we have to understand which is the area of this power screw and the nut assembly which is actually taking the main brunt of the force. Okay, so that area has to be understood. Okay, so in order to do that, we have to take a cross section. Okay, we have to take a proper cross section here and try to look at that particular diagram. Okay, so what I'm trying to do here is, after I take the cross section, this is something what I will look like, what it will look like, and what I'm drawing is the power screw. Okay, so the power screw has a certain outer diameter, and that is basically where the threads are, and obviously it has got a core diameter. Okay, so the core diameter would be visible somewhere here. Okay, so that is something like the core diameter, and then you'd have your outer diameter. Okay, and obviously, you have already know that generally the pitch circle diameter of the power screw is always told. Okay, the PCD, the pitch circle diameter. Okay, so the pitch circle diameter of the screw would be somewhere in between the core diameter and the outer diameter. Okay, so now this is, as I said, when we take a cross section and when we look from the top, that is how the cross section would look like. And here on this surface, on this entire surface of this thread, another surface of the nut, another similar surface of the nut would rest, and those two surfaces basically press on each other, and then there is wear. Okay, so in this cross section I can only draw one. So this is the area which is most important, the area between the core and the external or outer diameter, which is the one which is taking the entire brunt of the force. The pressure is coming on this area. Now in order to find the pressure is equal to force. In this case, if we are considering this as Q divided by area. Okay, so but it's not that simple here. It's not that simple. Q by A, but this area is not as simple as that. You just can't take this area of this annulus and go ahead and try to calculate the pressure. Okay, why? Because this is not the only area where engagement is happening. I just said earlier that this is the length of the nut, and in this length of the nut there are multiple threads, because this thing has a certain amount of the value of pitch is there, and there is certain length of the nut. Okay, so like these sections, there would be multiple cross sections where engagement between the nut and the screw actually happens. Okay, so this area gets added up, so this area gets added up. So how many times? So this area basically gets added how many times? So that will be found by, if L is the length of the nut and T is suppose the pitch of the thread, then L by T number of areas would be available. Okay, so if this is the total distance L and T is the pitch of individual threads, so if you divide that will give you the number of areas. Okay, so therefore that also has to be considered. And then finally you have got multiple start threads, so it's not a single start, so that again will come into the picture. Okay, so I think you've got a pretty good visualization right here, and what I will do here, I will go back to our slides, just a second, and we will try to take it off from here. Okay, so now we will see the design process. In this design process, we see that the equation that is given here by the book is something like this: P average is equal to QT by pi dH L into Z. Okay, so now let us see what those different parameters are one by one. The parameters are, the first one is Q, which is the pulling force. Then T is called the pitch of the thread that we have already discussed. Then the next one is D, is the pitch diameter of the thread, that also we just saw. H is height of the thread engagement. Okay, so that is again I will discuss that in just a little bit. And L is called the length of the nut that we just saw, and Z is the number of starts. Okay, so now I have already drawn a sketch here to try to elaborate what we are discussing. Okay, so here we already saw that this is the annulus. Okay, and the dotted line here basically that would basically be the pitch circle diameter. Okay, pitch circle diameter D. and the height of engagement of the thread is nothing but the distance uh, between the core diameter or the core surface and the external surface of the thread. Okay, so that distance is your h, which is given right here. Okay, so that distance is h. Now in order to understand the area, what we have to do here is very simple. You have to cut this annulus and you have to unfurl it. Okay, so when you unfurl this, you would find that it would become a rectangle like this. Okay, so this, it would be a rectangle like this, and what would be the length of this rectangle would approximately be equal to the circumference, this circumference right here. Okay, so that is given by pi d, and the thickness would be equal to h. Okay, so therefore in the formula you see that pi d and h have come, and that gives you the area of this cross section. Okay, so that is the area of this cross section. Okay, then I said, as I discussed earlier, this is not just one cross section, there are multiple cross sections. Okay, there are multiple cross sections here, and how do we know that? So we need to know the length of the thread L, and we know the pitch T. Okay, so what we understand here, it is that the number of areas would be L by T. Okay, so that L by T would have to be multiplied here. Okay, so then we take this T and bring it to the denominator, and it becomes your L by T. Okay, so therefore pi dh into L by T would be the number of areas, and a summation of that basically would give the total area. And then finally, lastly, you are multiplying this by z. Z represents the total number of starts that your thread has. If you have got 2 starts, that entire area gets multiplied by 2. Okay, so therefore this is the entire area, qt into pi divided by pi dhl into z. Okay, so that basically explains how we get average pressure on the screw and also on the nut. Okay, so this is how we calculate the average pressure. Now this pressure is then equated to the pressure that is derived from the design books, and then iterative design is done in order to fit the criteria. P average should be less than P average in bracket. We will continue with the other aspects of design in the next session. Thank you.